So today the primary goal is to start on the Electroweak hierarchy problem, but I did leave off one solution to the cosmological constant problem that a number of you asked about after the lecture yesterday, so I want to just spend the first 5 minutes going over it. And this is the idea of UV-IR mixing as a way of solving the hierarchy or the cosmological constant problem. So what's the idea? Well, one of the reasons why Dirac naturalness makes sense in a quantum field theory is that quantum field theories, in general, have the beautiful property of decoupling. This is what allows us to construct effective field theories, which is to say that we can define the quantum field theory at some fundamental scale, study it as it goes to lower and lower in energies, and if we study that theory at some particular slice of energy much lower than the original scale, we can describe that in terms of an effective theory where we've integrated out or coarse-grained over the high energy degrees of freedom. So there's a decoupling between ultraviolet modes and infrared modes in a well-behaved quantum field theory. That translates to the Dirac criteria of naturalness, because if you define a quantum field theory at some fundamental scale lambda, the theory at that scale can't know anything about the theory in the far infrared. This is what decoupling guarantees. And so it's sort of impossible for the theory defined at some fundamental scale to generate a much smaller energy scale, just because without something like fine tuning, just because decoupling guarantees it can't know about the infrared. Okay, so that's one reason. It's really decoupling in quantum field theory that makes the Dirac naturalness criteria so robust. But now you can ask yourself the question, OK, what if I wrote down some theory that violates this decoupling between the UV and IR, where somehow physics at different momentum scales is actually coupled in some interesting way? Then it might be possible for a theory defined at some fundamental scale to actually populate lots of different energy scales in a way that didn't involve fine-tuning. And we know that this sort of UV-IR mixing, it's not a property of four-dimensional quantum field theories that give us well-behaved EFTs, but it must be a property of a theory of quantum gravity. And the cartoon version, cartoon story you can tell yourself to believe that this is true is you can just say, well, let me imagine that I wanted to make a black hole by colliding two high-energy photons together, right? So you could take two photons of some frequency. If you get high enough frequency photons, you should be able to collide them together and make a black hole, right? OK. So now you say, great, so you made a black hole of some size by colliding those photons together. You're probing the ultraviolet of your theory. Now you say, I want to go to even higher energies. I want to study my theory of quantum gravity at even higher energies. So I'm going to take photons of even higher frequency, okay, and collide them together. That should make a more energetic black hole. So you do that. So these are my higher frequency photons. You collide them together, and what do you find? You actually make a larger black hole, okay? So you intended to probe the far ultraviolet of your theory of quantum gravity, but what you actually did was probe longer length scales by creating a larger black hole. So this is a sort of cartoon version of mixing between the ultraviolet and the infrared. And it is something that we expect is a property of our theory of quantum gravity. OK, so UV-IR mixing probably exists in a theory of quantum gravity. So the question is, how can you make use of it to solve what seem to be problems of effective field theory, all right, like these naturalness problems that we've been discussing? So the first thing you could do, of course, is come up with a complete theory of quantum gravity. Okay, so that's like solving a very small problem by solving a very big problem. So if you want to do that, be my guest. I won't stop you. But because we don't have a complete theory of quantum gravity, and there are many obstructions, I think, to getting there quickly, another thing you might do is come up with conjectured properties of a consistent theory of quantum gravity, and then ask if those conjectured properties actually place constraints on the allowed parameters in an effective field theory that descends from that theory of quantum gravity. So in an effective field theory, you might be allowed to have all sorts of different values of parameters, but maybe it's true that in a consistent theory of quantum gravity, only some of those parameters are actually allowed. OK, so from an effective field theorist's perspective, this would be a bizarre miracle. But from the quantum gravity perspective, this would be totally consistent. All right. So I want to give you one example in the context of the cosmological constant of a conjecture that you might make about the properties of a consistent theory of quantum gravity and the constraints that it might place on an EFT. And then we'll come back to it at the end of discussing the Electroweak hierarchy problem as well. So there have been lots of proposals about how to use UV-IR mixing in the cosmological constant problem. The first one I know of is from Banks in 1996. Incidentally, as you might have noticed from a lot of the discussion that I've made so far, often the first person to come up with many of these interesting and ambitious ideas is Tom Banks. So if you want to understand ideas that are beautiful and possibly before their time, you should read all of Tom's papers over the last 30 years. But the example that I want to give you is actually due to Cohen, Kaplan, and Nelson. So these are people that you might recognize. These are particle theorists. They're most famous in the particle theory community for things like working out the theory of electroweak baryogenesis, or certain versions of supersymmetric extensions of the Standard Model, or Nelson, of course, was the Nelson from Nelson-Bar. But actually, it turns out that this paper of theirs, which is not really well known in the particle theory community, actually has more citations than all of those other works, okay, just by different people. So their idea was the following. So as we know, the entropy of black holes is non-extensive. So the entropy of a black hole scales like its area instead of like the volume of the black hole. And that inspired Bekenstein to make a variety of conjectures about not just entropy bounds in gravity, but entropy bounds in quantum field theories. So these were conjectures that Bekenstein made, a series of conjectures ranging from 1973 to 1993. The precise form of the conjectures is not believed to be correct. It's been superseded by more precise conjectures. But for the purposes of this argument, we'll just take Bekenstein. OK, so Bekenstein's idea was inspired by the entropy of black holes, was to conjecture that even in field theories, the scaling of an entropy in a quantum field theory should scale non-extensively, should scale like the area instead of a volume. So if you consider a field theory in a box, the entropy should scale like the area of the box, not like the volume. But if you consider a quantum field theory as an effective field theory that has some cutoff, okay, and you put it in a box of length L, so 1 over L in some sense defines an infrared cutoff, and capital lambda defines an ultraviolet cutoff of this effective field theory. If you just compute in the EFT how the entropy should scale, it should basically go like it should be dominated by the highest energy of all of the modes in the box, fitting in the volume of the box. And so the entropy in an EFT does, of course, scale extensively. All right. Whereas Bekenstein's conjecture is that, in fact, for a consistent quantum field theory, the entropy has to be bounded from above by the entropy of a black hole of the same size, which is up to a factor of pi, just something that goes like the length squared of the box, with the Planck scale making up the factors of dimension. OK. So it seems naively, right, that an EFT, if this is how you're counting your degrees of freedom, that if this is true, if it's true that in any consistent quantum field theory, the entropy actually scales non-extensively, then an effective field theorist is vastly overcounting degrees of freedom, right? They're making a mistake, because in the field theory, this is how you would count the degrees of freedom. But something mysterious has to happen in the theory of quantum gravity that whittles out these extra degrees of freedom, OK? And so to make a consistent counting of degrees of freedom in your EFT, then a consistent EFT would satisfy the relationship that the entropy that you compute in the EFT satisfies this bound. In other words, it would satisfy the product of the cutoff cubed and the size of the box is no larger than the entropy counting that you get from black holes. OK. Now, immediately, this has a very interesting implication. So it tells you that now in a normal EFT, nothing tells you that the ultraviolet cutoff of the theory and the infrared cutoff of the theory are related. They are completely unrelated quantities, precisely guaranteed by decoupling. But satisfying this relationship now tells you, in fact, the UV cutoff and the IR cutoff are directly related to each other. In particular, the infrared cutoff of the theory is fixed. So it has to be of order. The size of the box has to be of order the Planck scale squared over the cutoff cubed. OK? So that's again, from the perspective of an effective field theorist, this is an insane miracle, right? Nothing in the effective field theory tells you this has to be true. So this is imposed by some consistency condition coming from the theory of quantum gravity that the EFT lives in. OK? Now, basically, this conjecture was made by Banks in 96. So what Cohen, Kaplan, and Nelson did was make a refined version of this conjecture. They noted that if you had an EFT living in a box, even if you satisfied this bound, there would be lots of modes in this EFT whose Schwarzschild radius was larger than the box itself. So basically, these things really shouldn't look like field theory degrees of freedom. If you're trying to study this field theory in a box, and some of the modes actually look like black holes whose Schwarzschild radius is outside the box, you probably shouldn't count them in your effective field theory. So they proposed a refined criteria that in addition to an EFT satisfying this, you also throw out all of the modes whose Schwarzschild radius exceeds that of the box. So that gives you a slightly refined criteria. So the Schwarzschild radius of the modes in the box, basically you could compute the Schwarzschild radius that fits inside the box. That's given by the largest energy density in the theory, the largest energy in the theory. So the largest energy density would be cut off to the fourth. The largest energy excitations in the theory would be cut off to the fourth times the size of the box. And then to compute the Schwarzschild radius, you're dividing out by m-Planck squared. So to require that you're only counting modes where the Schwarzschild radius of the mode fits inside the box, that tells you now, that gives you a sharper relationship between the size of the box and the cutoff, namely that the size of the box, or 1 over the size of the box being the infrared cutoff, is related to 2 powers of the cutoff squared. OK. So this was their conjectured relationship in any EFT that has some UV cutoff capital lambda, satisfying Bekenstein's entropy conjectures and only counting real field theory degrees of freedom inside this box actually forced you to correlate the size of the box with the UV cutoff of the theory. So again, something that doesn't occur at all in EFT, but you could imagine following a conjectured property of the theory of quantum gravity suddenly imposes an interesting extra condition. Now, the reason they wanted to come up with this refined constraint is if you take the size of the box to be the size of the visible universe, if you take it to be our Hubble scale as a length scale, then you work out, so if you take this to be the size of the universe, of the causally connected universe, then it turns out that the cutoff that you get is about 10 to the minus 3 electron volts. And so, of course, you know, if you take your CC to be the cutoff to the 4th power, this gives you the observed size of the cosmological constant. OK. Now, that's not actually satisfying from the perspective of an effective field theorist. From the perspective of an effective field theorist, the cutoff of your EFT, this is the scale at which something changes, something happens. OK. New degrees of freedom enter. The EFT description of the theory breaks down. You see something. So from an EFT perspective, even given this relationship that somehow correlates the IR and the UV cutoffs, to them they said, great, we should cut off all of our loops at 10 to the minus 3 electron volts. But I would still insist that I should see something new happen at this scale. We don't see something new happening at this scale. So to me, it's not a satisfying explanation. But I give it to you as an example. It's sort of the simplest example of if you imagine that a consistent theory of quantum gravity actually constrains the allowed parameters in an EFT, you can come up with interesting relations that violate naturalness arguments, that correlate things in ways that field theory wouldn't correlate them. Okay, and maybe that's what happens. Maybe actually the secret to these naturalness problems is violation of effective field theory, but violation of effective field theory that comes from the properties of a theory of quantum gravity. All right, so that's a very interesting idea. It's a very radical idea, but it's one that you should keep in mind is possible. Yes?
Is the statement that the entropy of any EFT should be less than or equal to that of a black hole, is that a conjecture or a theory?
That's a conjecture. This is Bekenstein's purely conjectured. And in fact, the particular conjectures that Bekenstein made are known not to be true, although they're now covariant entropy conjectures that are more complicated than this, but have a similar spirit. Okay. It turns out if you use those, you don't get the similar types of constraints. So I want to emphasize to you this conjectured relationship is falsified now. We know this, even if we know basically that this isn't true. Okay, and so even if you thought this somehow, if you surrendered your annoyance at the fact that new physics should appear here as a field theorist, even this relationship you shouldn't believe to be true. But the reason I tell you about this idea is that it is sort of, to me, the clearest illustration of how the properties of a theory of quantum gravity could constrain in a surprising way the allowed parameter space in an effective field theory. Okay? And I'll come up with another couple of sharp examples of that at the end of talking about the electroweak hierarchy problem. So with that, let's turn to the electroweak hierarchy problem. So what I want to do, I've got 2 more lectures today and tomorrow. And so today, what I mostly want to do is tell you about what the electroweak hierarchy problem is and what it is not, and tell you about the solutions that were on the market for most of the lifetime of the electroweak hierarchy problem. Of course, something has happened within the last few years, which is that the LHC has turned on and collected an astonishing amount of data. And for very interesting and non-trivial reasons, that data has placed constraints on those old solutions. And so on Friday's lecture, I want to tell you about solutions that have emerged more recently. Michael?
Let me ask you a question about the gravity physics.
Yeah.
So very often people say, you don't have to worry about, or maybe we have to worry more about the electroweak hierarchy because it's on the same footing as the cosmological constant. And did what you just said imply that there might be a purely gravitational solution of the cosmological constant problem, which, however, leaves the gauge hierarchy problem as a problem?
So the conjectured UV-IR mixing type of solution, so I should say there are conjectured applications of UV-IR mixing to both problems. No conjectured solution that I know of solves both problems simultaneously. So I would say my expectation would be UV-IR mixing gives you one and not the other. So for example, if it explains the CC problem, then the hierarchy problem is very likely to be solved by other things. Or vice versa, if the electroweak hierarchy problem is solved by UV-IR mixing, then the CC problem is likely solved by other things. But I know of no solution that does both. Okay. But on the other hand, I don't know that anyone has tried hard enough. The types of solutions I'll give you are both very specific to the two problems. Okay. So the electroweak hierarchy problem. So the electroweak hierarchy problem is very much like the problem that we started out with on Monday, Dirac's question of why is the proton much lighter than the Planck scale. The question, the electroweak hierarchy problem, in its simplest form, is why is the mass parameter of the Higgs, and also equivalently, why is the scale of electroweak symmetry breaking many orders of magnitude smaller than the Planck scale. Right? So this is 10 to the minus 34. If I use the Planck scale and not the reduced Planck scale as my figure of merit. Okay. Often you'll see 10 to the minus 32 if we're using the reduced Planck scale here. All right. That's actually one version of the electroweak hierarchy problem. The other version of the electroweak hierarchy problem, which is related, is one that was alluded to by Michael in his lectures this morning, which is that one thing we see is that this parameter is so much smaller than what appears to be the fundamental scale. But the other problem is that in the standard model, this scale is itself a parameter. It's not actually something that can be predicted in terms of any other quantities. Okay. These statements actually are related in interesting ways that I'll try to make clear through the rest of this lecture. But in some sense, when you're solving the hierarchy problem, there are sort of two things you could be trying to do. One is simply trying to explain this ratio without trying to make this into some fixed finite quantity you can compute or predict from first principles. But the other more ambitious thing you could do is try to make this quantity something that you can compute from first principles. And if you want to really understand the hierarchy problem and believe in all of its subtleties, you should try to do the most ambitious thing, which is to render this into a calculable quantity. And when you do that, whenever you do that, you'll find that all the things that we discussed today, all of the aspects of the hierarchy problem, become really unavoidable and can't be hidden in talking about how you regularize the theory or what happens in the ultraviolet. Okay. All right. So we know already that just seeing a ratio of mass scales need not be an enormous problem. So we saw, of course, that the proton mass could be explained by dimensional transmutation. It could be made Dirac natural. But we also saw, even as a sort of halfway point, that it would also be possible to make a technically natural ratio of scales. That is to say, a ratio of scales that could be at least explained by the violation of a symmetry. So for example, as we've already seen in great abundance, if I have a fermion, right? So the fermion, a Dirac fermion, there's a Dirac fermion mass term. And when I set this mass to 0, I restore at least the classical symmetry of the theory, which is the chiral symmetry under which I do axial rotations of the Dirac fermion, right? So it is easy to understand why, if you have a Dirac fermion, the mass parameter is technically natural, because when it's taken to 0, there's an enhanced symmetry, namely the axial symmetry of the theory. Okay. The problem is, for the Higgs boson, the Higgs doublet in the standard model, the mass parameter is m squared mod h squared. And this parameter, there are no symmetries of the standard model or of any extension of the, well, there are no symmetries of the standard model that are made manifest when this parameter is taken to 0. So when this parameter m squared goes to 0, there's no enhanced symmetries. And so it's just not possible. That's just because this is a total singlet under all gauge global Lorentz symmetries. And so there's simply no technical naturalness way of justifying the lightness of the Higgs relative to some fundamental scale. OK. So the Higgs mass parameter is not technically natural. And therefore, we really are trying to explain either as an intermediate step, try to make this technically natural so that this hierarchy is at least guaranteed by some symmetry structure, or more ambitiously to make this entirely natural to explain the numerical value of the ratio as well. OK. So our Dirac naturalness explanation, if we take the standard model up to some fundamental scale capital lambda, the Dirac naturalness explanation, or expectation, of course, is that this thing should be of the order of that scale squared. And just like in the case of the cosmological constant, we can justify that by computing radiative contributions to the Higgs mass parameter. So very often what's done is to say, let's take the standard model up to some momentum cutoff, associate the momentum cutoff with the fundamental scale, and then compute the radiative contributions just from loops of standard model particles. So that means, compute the 2-point function of the Higgs at one loop. It gets various loop corrections coming from all of the quarks and the gauge bosons in the standard model and from the Higgs itself. And so if you sum over all of those contributions, integrating up to some cutoff lambda, what you get is something that depends on the cutoff, and then contributions of various particles in the standard model. So there's a contribution from the Higgs itself. So this is coming from diagrams of this form. All right, that's proportional to the Higgs self-coupling. There's a contribution from electroweak gauge bosons. And then there are contributions from the fermions. And most notably, as Michael discussed this morning, the top quark has the largest coupling to the Higgs boson because it has the largest mass from electroweak symmetry breaking. And so that's the dominant contribution from fermion loops. So if you look, of course, at all of these things numerically, the Higgs self-coupling is about an eighth. These couplings are 1 over a few. This is order 1, and so the largest contribution is coming from top loops. Okay, so this seems to bear fruit, or at least to justify this naturalness explanation. This naturalness expectation that radiative contributions computed in the standard model up to some scale give us up to a loop factor or something of this order. Now, there are two things that should make you uncomfortable about this. So very often when people talk about the hierarchy problem, they say, oh, the Higgs mass parameter is quadratically divergent. This is the quadratic divergence. Deal with it, right? Most of you, is that the first way you heard about the hierarchy problem was that sort of thing? Certainly for me, that was it, right? Quadratic divergence, deal with it, OK? So there are two things that should bother you about this, right? The first is that it's not obvious that you really have to consider the standard model as an EFT up to some cutoff, right? So let's set aside gravity for the moment. The standard model appears to be a perfectly consistent quantum field theory. As Michael has said, it is the most general theory consistent with the observed particle content, gauge invariance, and normalizability. So it's not obvious that I have to imagine that this theory was defined at some fundamental scale in the UV. Maybe I just take the standard model and I can run it up to arbitrarily high scales. And then there's really no significance that I could attribute to doing some momentum integral up to a cutoff. Okay? So that actually turns out not to be true. So can anyone who didn't go to PITP last year tell me why that's not true? Why the standard model is not UV complete on its own? Setting aside also neutrino masses. Okay. Silly neutrino masses. Anyone? So I started my first lecture talking about the logarithmic evolution of couplings, of gauge couplings. So we saw the SU3 gauge coupling got larger as we went to lower energies. That was a surprise, because until people computed the beta function of Yang-Mills theory, the beta functions that they had computed were of Yukawa interactions and also for abelian gauge interactions. And those both had the property that they decreased at low energies, or conversely increased as you went to higher and higher energies. All right, so now can anyone guess why the standard model is not UV complete? You went to PITP last year. All right.
Because of the Landau pole in the U1?
Yes, because of the Landau pole in the U1. So if I run hypercharge, right, so the hypercharge coupling, just like the QCD gauge coupling, evolves as a function of scale. I can write down the renormalization group equations. So the leading piece is 41 over 10 plus higher order pieces. Now, the hypercharge gauge coupling, especially when I've divided out by powers of 4 pi, is very small. So this running is very slow. The logarithmic evolution is very slow. But what happens is if you start with the measured value or the inferred value of the hypercharge coupling at the z-pole, okay, and then you just run it up to higher and higher energies, what you find is eventually it does the converse of what the QCD gauge coupling did. QCD gauge coupling blew up in the infrared. This blows up in the ultraviolet. It blows up after a very long time. And the scale that happens, depending on how you do it and what precision you want to do, is about 10 to the 41 GeV. Okay. So the standard model, if you leave it to its own devices, does something terrible to itself in the far ultraviolet. And normally we don't worry about this because we say lots of other things happen before we hit that scale. So, most notably, the Planck scale, the scale where we think quantum gravity becomes strong, is a much lower scale, 10 to the 18 GeV. And suggestively, the standard model gauge couplings seem to coincide at a scale that's about 10 to the 16 GeV. And if they coincide, then we think there's some grand unification in which all these factors combine into a non-abelian factor, and that non-abelian factor runs differently. Okay. So normally we think that something else happens and avoids this problem. But even if you wanted to imagine that nothing else happened in the ultraviolet of the standard model, there was no gauge coupling unification, there was no new physics at the scale of quantum gravity, the standard model would kill itself. Okay. And something else would have to happen, something new would enter the picture, and so you should treat the standard model as an EFT. Okay. So that's one thing. The second thing that should bother you, of course, is that when you learn about renormalization, you learn that these divergences are not really physical, right? They are artifacts of how you decide to do the calculation. In particular, the form of the divergence is an artifact of how you parameterize the divergence or how you parameterize these loop integrals. And that what you ultimately do is define some regularization conditions and renormalization procedure that absorbs the divergences and gives you physical quantities as a result and simply relates physical quantities to each other computed at different scales. And so very famously, something that people like to say is, go ahead and compute these loop diagrams in dimensional regularization where there's no cutoff. All you have are 1 over epsilon poles. And then there's no hierarchy problem. Okay. Now that's deeply mistaken, but in a way that we have to think about in a little more care to understand why. So what I would tell you is when people write down this quadratic divergence, it is a stand-in for physical and physically calculable effects associated with some much higher scale. It's not associated purely with the high momentum modes of standard model fields. That's what it looks like from this calculation. But it's actually a stand-in for new things that happen at this scale. And if you put in any specific details about what new physics happens at this scale and repeat the calculation, what you find is it's not a matter of cutoff dependence. It's a matter of actual dependence on real physical quantities that you can calculate. Okay. So that's what the hierarchy problem is. It's not quadratic divergences. This is just a signal that the Higgs mass parameter is sensitive to physics in the ultraviolet. And anytime you specify that physics, you can instead do this calculation and get a finite answer, but one that bears out this expectation. Okay? And this also is justified if you take the more ambitious framing of the hierarchy problem, that you want to make the Higgs mass parameter finite, something you can predict from first principles. Anytime you extend the standard model to make the Higgs mass parameter calculable, this doesn't exist. There's no more UV sensitivity, but it's replaced with finite contributions that come in at the scale of whatever new physics made the Higgs mass finite and calculable. Okay, so that's the hierarchy problem. So now you don't have to ever be confused. It's not quadratic divergences. If anyone tells you that, you should poke them until they give you a better answer. Okay. So let's talk about a more specific example. Let me just give you a simple toy model to help understand what this quadratic divergence is actually signaling, how it could actually be sensitivity to some higher scale. So to do that, let me just give you a simple toy model. That's just a toy model, the simplest toy model I could think of, which is a toy model consisting of a real scalar and a Dirac fermion in 4 dimensions. So that theory consists of the kinetic terms for the scalar. Okay, just a real scalar, so relatively straightforward. We can add a mass for the scalar, so I'm going to write this as little m. We can add a self-coupling for the scalar, although this is not going to be important in what follows. But you can't accuse me of being inconsistent. And then we're going to add a Dirac fermion. We're going to allow a mass term, so let me call this big M for the Dirac fermion. And then we're going to add a Yukawa interaction that couples the scalar to the fermions. Now, if I'd been more ambitious and started with a theory of a complex scalar, then this would actually be very familiar from the theories that we were talking about for the axion that have a PQ symmetry. So if we'd taken the mass term for the fermions to 0, I could do axial rotations of the fermions that could be respected by this Yukawa interaction if the scalar also transformed under it. But because for simplicity and to get my factors of 2 right, I picked a real scalar. Instead of having a continuous axial symmetry in this problem, there's actually just a discrete axial symmetry of the Dirac fermion goes to gamma 5 times itself, and the scalar goes to the minus scalar. Okay. So this is just a baby version of a Peccei-Quinn symmetry. It's a discrete version of a Peccei-Quinn symmetry. But you'll notice this should guarantee that if I took the fermion mass to 0, there would be an enhanced symmetry, which is this would be a good symmetry of the full theory. So this mass parameter is technically natural. But this symmetry says nothing about the mass parameter of the scalar, okay? Because phi squared is invariant under phi goes to minus phi. All right. So now what I want to do is if this is our theory defined in the far ultraviolet, what we want to do is study it as we go to lower and lower scales. And in particular, what I want to imagine is that the fermion is much, much heavier than the scalar. So as a good effective field theorist, what I do is I take my theory in the UV, I evolve it down to the mass of the fermion, then I integrate out the fermion to get a low energy effective theory that just consists of the scalar. And the parameters in that low energy effective field theory are going to be fixed by a matching procedure that I carry out between diagrams in the full theory at the scale m and diagrams in the effective theory at the scale m. So formally what I do is I want to match the one light particle irreducible diagrams between the UV and the IR across the scale. Okay. So again, if I want to imagine the scalar mass is much less than the fermion mass, I now want to construct an EFT at the scale big M that just consists of the scalar. So to do that, the first thing I can do is I can match the 2-point function. So in the full theory, there's of course a tree level contribution to the 2-point function from the scalar. That's true in both the full theory and the effective theory. So I'm not going to bother about that in the matching. In the full theory, there's also radiative corrections to the 2-point function. For example, coming from loops of this heavy fermion contributing the 2-point function to the scalar. And I'm going to match this to a correction to the 2-point function of the scalar in the EFT. Okay. So I can go ahead and I can compute this diagram. This is a good exercise to the reader. I picked a real scalar because I always get confused with the factors of 2 for a complex scalar. So what is this? This has the form in its full glory of it's of course proportional to the square of the Yukawa couplings. There's a loop factor. There's some multiplicity factors. And then it has the interesting following features. So there's a divergent part. If we do it, so I should specify, of course, anytime you construct an effective field theory, anytime you do this running and matching, you of course need to specify your renormalization, your regularization scheme, and your renormalization procedure. So we're going to do this in MS bar, which, as Michael has reminded us from this morning, is a sensible scheme in which to construct and talk about effective field theories. So there the divergences are parametrized by 1 over epsilon poles. There's no quadratic divergences, right? So we have no confusion about quadratic divergences. So there's something that depends on the regularization parameter epsilon. Here I'm going to soak up the factors of 4 pi and Euler gamma that show up for my regularization. And there's some finite pieces and some logarithmic pieces. There is a dependence on the renormalization scale because there's a logarithmic divergence. This all multiplies a combination of the heavy mass and the momentum of the particle. And then there's some other finite pieces. Okay. So now I want to match this to the Lagrangian of the EFT so that I can reproduce in the EFT at the scale, renormalization scale equal to big M, I can reproduce all of these features. Okay? So I can do that. And what I find is that the Lagrangian, so I do my matching, of course, at the scale mu is equal to big M so that I kill off these logarithms. And what I find is that the Lagrangian for the light scalar in the EFT picks up a correction to its kinetic terms coming from, well, there's some additional higher order contributions that are proportional to p squared here. That multiplies, you can think of this as a wave function renormalization of the scalar in the EFT. And then there's a shift to the mass that's just coming from these. Let's see, did I drop a bracket? That's coming from this contribution living in front of the fermion mass appearing at one loop. And so that you can interpret as a shift in the scalar mass. Okay, so what do I see? From the perspective of a low-energy effective field theorist who's just studying this theory of this light scalar well below the mass scale of the heavy fermion, I see that the mass parameter of this scalar has contributions, one that is proportional to whatever the ultraviolet value of the scalar mass was, whatever I fixed at the fundamental scale when I defined the theory, shifted by an amount that is proportional to a threshold correction coming from the mass of the heavy fermion. Okay, so that is to say, even if I wanted to make the mass of the scalar arbitrarily small in the ultraviolet, the low energy effective theory of the scalar contains an effective mass for the scalar that can't be much slower, can't be much smaller than a loop factor down on the mass of the fermion. Okay? Now, if instead I had just said, let me take this theory and let me compute, up to some cutoff loops of the fermion contributing to the scalar mass, I would have had a quadratic divergence, right, up to some hard cutoff, that also would have had this form. Okay, so that's what the quadratic divergence is doing. Anytime you do a calculation with a hard cutoff, you get a quadratic divergent piece. What it's telling you is there's UV sensitivity, and if there are particles in the ultraviolet of the theory, okay, they actually come in when you include them and do the calculation carefully. They give you finite contributions you can calculate that have the same parametric form as the quadratic divergence. Okay, so here it's not a problem of quadratic divergences. It's just that if I had actual physical states at higher masses, it's very hard for my low energy effective theory to have parameters in it that are very different from these high scales. Okay. Now, you can flip the calculation. You could say, let me instead construct an effective field theory of a light fermion, where I imagine instead I'd taken the scalar to be heavy, and I wanted to write down the effective field theory of the light fermion. And you could repeat this exercise computing radiative corrections to the two-point function of the fermion. And what you would find in that case is that the corrections of the fermion mass are proportional to the fermion mass itself and not to the scalar mass. And that's because the fermion, right, the mass parameter is technically natural. There's a chiral symmetry of the theory that is manifest when the mass is taken to 0. And that's what guarantees that even when I do this matching in my EFT calculation, there's not going to be a correction to the fermion mass proportional to some other scale. Okay, it's because of the chiral symmetry that protects the fermion mass. Corrections to the fermion mass have to be proportional to chiral symmetry breaking. Okay, so this is a nice example to understand why the hierarchy problem is a problem and why it's a problem for the Higgs and not for some, say, other fermions in the theory. All right. Now, so even if you were only worried about the first form of the hierarchy problem, why is the Higgs mass parameter much less than the Planck scale, even if you didn't worry about making the Higgs mass parameter finite, one thing that would bother you immediately is even if something mysterious happens at the scale of quantum gravity, the standard model is eaten up into some complicated string theory, we have reason to hope or expect that there are lots of different field theoretic scales that the standard model encounters on its way up to the Planck scale. And each one of those field theoretic scales would be associated with threshold corrections of any particle that talked to the Higgs. Okay. So a good example of that is just thinking about the physics of grand unification. So again, I mentioned to you that if you take the standard model gauge couplings as they're measured down at the weak scale, and you run them up to higher and higher energies, what you find is they ultimately appear to cross at a scale in the standard model it's about 10 to the 15 GeV. There are reasons to want that scale to be somewhat higher that we can go into if you'd like. But they appear to cross at some scale. And the natural hypothesis is that the standard model gauge couplings are unified into a simple gauge group at that scale. Okay? So what that means is if grand unification happens, there are heavy gauge bosons that are associated with extending the standard model gauge bosons into a more unified set. And now I can think of if I start in the far ultraviolet of my unified gauge theory, and then I explore the theory at lower and lower energies, I go through the scale of grand unification, and I enter the standard model as an effective theory. I can repeat this calculation of the corrections to the Higgs mass squared parameter coming from heavy particles associated with grand unification. So in particular, there are heavy scalars associated with extending the Higgs to live in a grand unified multiplet. And then there are heavy gauge bosons. And so they go ahead and combine to give a contribution to the Higgs mass parameter. So there's some heavy scalar triplets that are required to unify the Higgs into a complete multiplet. And then there's some extra heavy bosons, let me call them X, that are required to fill out a complete adjoint of a grand unified gauge group. And these things all have masses of order the unification scale 10 to the 15. So you can go ahead and you can do this calculation. So this gives a correction, for example, a threshold correction to the Higgs mass that's of order the unified value of the standard model gauge couplings times this unification scale squared. OK. So if that scale is 10 to the 15 or 10 to the 16 GeV, this is some enormous correction to the Higgs mass associated not with some ambiguities about quadratic divergences, but with very real physics that happens at a higher scale. OK. So if you want to believe that anything happens above the weak scale before you hit the theory of quantum gravity, you're forced to contend with these contributions, even without worrying about making the Higgs mass parameter finite in some extension of the standard model. OK. Any questions? All right. There are other examples of fun things that correct the Higgs mass. I'm going to leave them in the notes and move on. So the Electroweak hierarchy problem is in somewhat of an intermediate footing between the cosmological constant problem and the strong CP problem. So the strong CP problem, we saw it was a dimensionless parameter we were interested in making small. And we could write down extensions of the theory that explain the smallness of that parameter, where the new physics or the signs of the new physics were very weakly coupled. So in particular, the Peccei-Quinn symmetry breaking scale could be much higher than the weak scale. The axion could be very weakly coupled. In the parity solutions, these new particles could be much heavier than the weak scale. So that had the advantage that we could solve the problem and not necessarily have any direct evidence for it that we could look for right now. The CC problem was on the other side. The CC problem, the scale is 10 to the minus 3 electron volts. So anything that you wanted to do to solve the cosmological constant problem, apart from doing very crazy things, you would expect new things to show up at the scale of the observed cosmological constant. And of course, we don't see anything like that. So that's a real pressing and very hard to understand problem. The Electroweak hierarchy problem is very interesting because if you take this, the EFT calculation of the quadratic divergence, if you say, look, if I expect the standard model to get new corrections from the ultraviolet that are of that size, then I expect something to happen to the standard model at a scale so that those loop contributions are not much larger than the value of the Higgs mass parameter that we see. Right? Then the Higgs mass parameter would be natural. Okay, so if the standard model, something happened to the standard model at some scale lambda, if those radiative contributions of the Higgs mass parameter were not much larger than the value that we see, then we wouldn't have a problem. And so in the standard model, if you just take this, the one loop quadratic divergence, and you ask, what is the size of lambda such that these corrections to the Higgs mass parameter are of order the Higgs mass parameter that we see, then that tells you that this cutoff scale, the scale where something changes, has to be about 500 GeV. So what you should do is expect that however you extend the standard model to solve the hierarchy problem, something should change in the picture not far above the weak scale. And that turns us into a very interesting strategy, right? Because we're only now starting to explore physics at and above the weak scale. So you would hope that whatever solves the Electroweak hierarchy problem, you would really start to be probing in the modern era. And that makes it very interesting. All right. Now, before you bet your entire career on trying to write down solutions to the Electroweak hierarchy problem, you would like this strategy to be justified by something, right? If the strategy is you want to solve the hierarchy problem, you want to write down a theory that solves these problems, and you know it should show up at some scale that's not far above the weak scale, you want to know that this somehow was a good idea based on past examples, right? Otherwise, it just seems like it's like a story that someone tells you, right? And you don't know if it's true or not. You're just taking it on theory. So let me give you two examples of how this strategy of taking the EFT calculation to get a mass correction, using that to signal a scale, using the observed value of a mass parameter to figure out the scale at which new physics had to enter, and then looking for that new physics. Let me give you two examples where that turned out to be exactly the right idea. Okay. So the first one is in the mass splitting between the charged and neutral pions. So as we've alluded to, and as hopefully you already know from your experience as a high energy physicist, the pions and kaons are goldstones of spontaneous breaking of chiral symmetries when QCD confines. They acquire mass because the symmetry is not exact. It's broken by the quark masses. And so they're not exactly massless, but they're lighter than the rest of the QCD excitations. Okay. But famously, the symmetries that are spontaneously broken to give these pions as the goldstones, those symmetries are also broken by electromagnetism. Okay? So we observe actually in nature that the difference between the squares of the charged and neutral pion masses is 35.5 MeV squared. Okay? And we actually have a reason to hope that we could understand this, because in the low energy theory of the pions, there's also a photon floating around. Because the charged pions are charged, they couple to the photons. The neutral pions don't. And that coupling violates the global symmetries that are protecting the masses of the pions. So that means there's a diagram that contributes to the charged pion masses that corresponds to a photon loop. Okay? And this analogous diagram doesn't exist for the neutral pions because they're neutral. Okay. So I could do the same thing I did for the standard model. I could say in my low energy theory of this pseudoscalar, there's some particle that couples to it a photon, and I can compute up to some cutoff the contribution of the pion mass coming from this loop. Okay, so I get this is about a correction to the charged pion mass. That's a factor of 3 times the QED coupling, 16 pi squared, and it's quadratically divergent, so it goes up to a cutoff squared. Okay. So now if you say, all right, this is a contribution to the charged pion mass, but not the neutral pion mass. If I want this contribution not to exceed the observed splitting between the charged and neutral pion masses, what does that have to say about the cutoff scale? Okay, so you can go ahead and work out the numbers, and it tells you for this contribution to be the size of the observed splitting, the cutoff has to be about 850 MeV. And lo and behold, right before you hit the scale, as you study the physics of the chiral Lagrangian, and you study the physics of pions as you go up to higher energies, you hit the rho meson. The mass of the rho is at 770 MeV. And the rest of the spectrum are vector mesons. And those, in some sense, those constitute a new contribution to the chiral Lagrangian, where if you compute those diagrams, it cuts off the divergence coming from the photon and gives you a finite answer proportional to the rho mass. Okay. So this is a case where this naturalness strategy was perfect, right? From the low energy effective theory, you had a scalar or a pseudoscalar, had a quadratically divergent contribution in the EFT. You say, OK, if new physics enters at some scale, the contribution of the mass shouldn't be bigger than the observed quantity. I use that to predict new physics at some scale. And sure enough, nature complies, right? It puts in new physics, cutting off this divergence exactly where it needed to. Right. Now, this is a bit of a post-diction because we knew of the existence of all of these mesons before we told this story. But an even better version of the success of this strategy is the mass difference between the k long and the k short. So famously, there's a mass difference between the k long and the k short. Which is best written in the following form. So we conventionally write it in terms of G Fermi, the k-on decay constant, which is 100-ish MeV. And if you did this calculation in a theory where you only had 3 quarks, so where is this coming from as a calculation that you do in the theory of QCD that you match on to the kaons as asymptotic states? It comes from doing a calculation. There's a loop diagram involving electroweak gauge bosons. And if you only knew about 3 quarks, so if you only knew about the up, the down, and the strange quark, and you put those as things that could run in this loop with W bosons crossing the lines here, you would find that this was quadratically divergent. And so you would get a contribution of the mass splitting that was proportional to the cutoff square. Okay? And so we actually know this mass splitting, this quantity is observed to be about 7 times 10 to the minus 15. Okay? So if again you repeat the argument and you say new physics is going to enter at a scale that makes this mass splitting the size of the observed splitting, then you would say that the cutoff scale where new physics enters should be about 2 GeV. And what's the mass of the charm? Michael told it to you this morning. What's that? The charm quark. What's the mass of the charm quark? 1.2. Yeah, good. So the charm enters. The fourth quark flavor enters. And when you introduce the fourth quark flavor into this diagram, it renders the diagram no longer quadratically divergent. Okay, and it gives you an answer that's proportional to the square of the charm mass. So this was actually a successful application of the naturalness strategy in history. So Gaillard and Lee used precisely this rationale to predict the mass of the charm. Okay, not so bad. Michael, you have a better grasp of this history than I do. Oh, fantastic. You'll have to explain to me that example in more detail later. I'm always on the lookout for more ammunition. Okay, very good. All right, I'll have to be more careful about how I use this example then. Okay, so that's the strategy. And so now the question is, okay, how do we put it to work? Can we write down extensions of the standard model that allow us to solve the hierarchy problem either by just explaining why the Higgs mass parameter is small, or better, by actually rendering the theory finite and giving us a calculable version of the Higgs mass where new physics is entering around this scale? Okay. So there are basically three things you could try to do, or the three things that people have tried to do over the 40 years that we've been grappling with the electroweak hierarchy problem. So I'm going to sketch those for you today, and then I'll sketch the newer solutions that have emerged in the last 5 years or so. I'll sketch those for you tomorrow. But there's basically three things you could try to do to explain the smallness of the Higgs mass parameter. And it's easiest to understand how those things work just by making a cartoon. Okay. Well, in fact, I'll skip the cartoon in the interest of time. Nobody likes cartoons anyway. So what was the problem? So the problem was there is at least some radiative correction of the Higgs mass parameter that's proportional to some cutoff. That cutoff can't be too high, so new physics has to enter at some low scale. So there's three things you could do. The first thing you could do is you could just lower the cutoff of the standard model so that either the Higgs itself ceases to be an elementary scalar field in the standard model at some very low scale, or that the whole standard model ceases to become some valid four-dimensional effective field theory at some low scale. Okay, so you can do this just making the Higgs into having the Higgs have a very low cutoff as a scalar field theory. That's what we call Technicolor. So Technicolor is trying to just use Dirac's observation, or to understand the mass of the proton being much less than the Planck scale. The reason for that is that the proton is a bound state, and the scale of the bound state is given by this dimensional transmutation. So you could say, great, that worked once. No reason why it can't work again, right? And you would say, great, the Higgs is a bound state of some new confining interactions whose confinement actually breaks electroweak symmetry. All right, that would be Technicolor. You could also imagine erasing the standard model as a valid four-dimensional theory by extending the theory into extra dimensions, either having large flat extra dimensions or having warped extra dimensions. Those, in particular, warped extra dimensions is holographically dual to Technicolor, so it's really the same solution. Okay, so lowering the cutoff is one example. The second possibility is to do what we've done so far to explain other small mass parameters. So fermion masses are rendered at least technically natural by chiral symmetry. So to extend the standard model so that there's a symmetry that now acts on the Higgs mass, so the Higgs mass parameter becomes technically natural. And the third possibility is, just as we've seen with the cosmological constant problem, to see if there is some anthropic explanation. So if you can find some bound on either the scale of the Higgs or the scale of electroweak symmetry breaking, where if we varied beyond that bound, we would cease to be able to form structure and observers. Okay, so these are sort of the traditional three solutions. I'm not going to spend much time at all on lowering the cutoff. It's a beautiful idea, and there are many beautiful models that have been constructed around it. But there are sort of two problems with just lowering the cutoff of the theory. One is that in addition to the radiative corrections that we saw, where you computed standard model loops up to some scale, if you just lower the cutoff and either the Higgs becomes a composite degree of freedom or the entire standard model goes into some extra dimensions, what you typically predict is that there's no loop factor between the Higgs and the scale of new physics. So in addition to the loops that we computed for standard model fields, there should just be a bare contribution to the Higgs mass that sort of order the scale of the new physics. So that really tells you if lowering the cutoff explained the mass of the Higgs, you should see things right on top of the Higgs mass. Okay, violent things should be happening right where we see the Higgs. And we don't see that. Okay. Not only do we not see that, we don't see any evidence for higher dimensional operators that correct the standard model. So non-normalizable corrections to the standard model that Michael will tell you more about tomorrow. We see no evidence for those. And those would be appearing with scales not much higher than the Higgs mass itself. Okay. So the non-observation of any of those corrections really disfavors purely lowering the cutoff. If you want to make the Higgs mass into a natural parameter, a technically natural parameter, by extending the standard model so that there's a symmetry acting on it, the good news is there's only a finite set of possibilities. So we have the Coleman-Manjula theorem and its extension by Haag, Sonius, and Lopazansky. Okay, so the Coleman-Manjula theorem is the statement. Who doesn't know the Coleman-Manjula theorem, actually? It's OK if you don't. OK. Well, we should do a better job of teaching you field theory. But the Coleman-Manjula theorem is a beautiful theorem that tells you that in addition to Lorentz symmetry, the only other possible symmetries you can have are what bosonic symmetries is what Coleman-Manjula knew about, are scalar charges corresponding to global symmetries. Then and potentially if particles are massless, you can also have conformal symmetry. Haag, Sonius, and Lopazansky knew about spinorial charges, and so that also allows you the possibility of supersymmetry. So it's not as though there's an infinite zoo of symmetry solutions to the hierarchy problem. The options are basically global symmetries or supersymmetry. OK, so let me explore both of these briefly, and then we'll close talking about anthropics. So supersymmetry, you're going to have a series of 4 lectures from Yael Shadmi, who will lay out in glorious detail supersymmetry and how it works. The way you should think about supersymmetry is it is just an extension of the Poincare symmetry to include some spinorial charges. Okay, so some charges that transform like spinors. And there's a very natural, once you say, I want to add some spinorial conserved quantities to the Poincare algebra, there's a very unique way of doing that. And for what follows from that, just as once you take Poincare symmetry, you can classify the irreducible representations of Poincare. So that's what gives you the idea that quantum field theory should have fermions and scalars and vectors. You can ask, what is the classification of irreducible representations of the super Poincare algebra? And the idea is now you should have multiplets of supersymmetry that involve the familiar objects, scalars and fermions and vector bosons, but now combine them, particles with different spins, into the same multiplet that transforms into itself under supersymmetry transformation. All right, so we don't have time to go into that into great detail, and Yael will tell you a lot more about that when she lectures next week. But the basic idea is that a supersymmetry transformation will take, for example, a scalar under a small infinitesimal SUSY transformation. We'll take it into a small SUSY transformation where this infinitesimal SUSY variation is actually proportional to some spinorial symmetry transformation parameter and some fermion theory. So the supersymmetry transformation takes a scalar into a scalar shifted by a fermion. And it also takes, for example, the fermion into the fermion shifted also by the scalar. Okay? So being uselessly pedantic, this is also proportional to the spinorial symmetry transformation parameter. OK. So supersymmetry is a symmetry that relates bosons and fermions. And the basic idea, it's actually clear once you just say those words how supersymmetry could solve the hierarchy problem. Okay? So the Higgs doublet living in the standard model is going to be related now to a fermion. In fact, there's an interesting subtlety that in the minimal supersymmetric extension of the standard model, you have to have 2 Higgs doublets. So Michael told you about the possibility of more Higgs doublets this morning. In supersymmetry, you have to have 2 Higgs doublets. Can anyone tell me why that is? Oh, no, someone said anomalies. OK, that's one of the 2 reasons. All right, there's a second reason. Yeah.
Each dagger can't appear in the
Good, OK. So that's more subtle, and I don't want to go into that. But there's two interesting reasons why you have to have two Higgs doublets in the supersymmetric theory. The basic reason, the simplest reason at the level of our discussion is anomalies. So if the Higgs doublet is going to be related to a fermion, it's going to have the same quantum numbers by supersymmetry. We know the standard model itself has no gauge anomalies, no cubic gauge anomalies. If I added a new fermion that was charged chirally under the standard model, I would now spoil anomaly cancellation. So to restore anomaly cancellation, I have to add another fermion of conjugate quantum numbers. And that new fermion should then come with a Higgs of its own. OK. So the minimal supersymmetric extension of the standard model has two Higgs doublets in them. But now those Higgs doublets are related by supersymmetry to fermions. OK. And we know that fermion masses are technically natural because of chiral symmetry. So that's what SUSY is doing, right? SUSY is basically lending the chiral symmetry of the fermions to the Higgs. OK. So that's how you should think about supersymmetry, at least making the Higgs mass parameter technically natural. Now, supersymmetry, of course, what it would predict if it were an exact symmetry of nature, it would predict that the masses of every particle in the standard model would be exactly degenerate with the opposite statistics particles predicted by the symmetry. And you can see that if you just write down the supersymmetry algebra. In particular, in the supersymmetry algebra, energy momentum vector p squared commutes with the spinorial supercharges. So that tells you that the masses of all the particles in a given supersymmetry multiplet have to be the same. OK. Of course, we go out in nature and we don't see a scalar electron degenerate in mass with the electron. And so we have to break the symmetry by some amount. And we do that by writing down basically dimensionful parameters that violate the symmetry. OK. So as Michael already told you this morning, in the standard model, of course, all the fermions are chiral. We can't write down masses for them until we break electroweak symmetry. But if we introduce scalar partners for those guys, the scalars can have mass terms that don't break any symmetries of the standard model. OK, so for example, if I have, say, a right-handed electron in the standard model, by supersymmetry, it's going to be related to a scalar, which we call this electron. And nothing prevents me from writing down a mass term. The symmetries of the standard model don't prevent me from writing down a mass term, the modulus squared of this electron squared. OK, so supersymmetry would prevent that. But the gauge quantum numbers in the standard model allow this. And it generally allows it for all of these new scalar partners predicted by supersymmetry. So if these mass terms are present, they break the symmetry. But they break it in what we call a soft amount. Because if I want to now compute any radiative corrections coming from this breaking, the mass dimension of any of those radiative corrections, say to the Higgs mass parameter, is going to be saturated by the dimensionful parameter that breaks the symmetry. So there's no room for quadratic divergence to enter just by dimensional analysis, right? If I compute, for example, the correction to the Higgs mass coming from loops of this electron, if supersymmetry were exact, this would cancel against a contribution coming from the right-handed electron. Now there's a breaking of the symmetry, but it's proportional to a dimensionful parameter. And so this loop will correct something at order mass squared. And this is the only thing that could enter. OK, so we break the symmetry, but in a way that doesn't reintroduce UV sensitivity. The clearest way to see that is to focus on the most important radiative corrections to the Higgs. So in particular, we saw already the thing in the standard model that couples to the Higgs with the largest coupling is the top quark. And in a supersymmetric theory, then of course the top quarks have their own scalar partners, the stops. This is why it's fun to be inventing names for particles in America, because we get to make very ridiculous names. All of the particles in the supersymmetric extension of the standard model have very funny names. But so how that works is, so now you could go ahead and compute in a theory that consisted of the top quarks, so top left and top right, and also consisted of their supersymmetric extensions, the scalars, the stop left and stop right. You could go ahead and repeat this calculation that we did, imagining the standard model to be an effective theory up to some cutoff, where now you compute the loop corrections coming from all of these particles. And so what you would see is, in addition to the diagrams we already computed, so this gave us minus 6 times the top Yukawa coupling squared over 16 pi squared, integrated up to some cutoff. Now there's also diagrams that have these new scalars running in the loop. The couplings of these scalars to the Higgs are dictated by supersymmetry. They're related to the couplings to the top quarks. So the diagram looks like this. The couplings are related. And because this is a fermion, this is a scalar, there's a minus sign in the loop factor here relative to this. This contribution is plus 6 y top squared over 16 pi squared. So of course these cancel, as they must have, right? We already said supersymmetry is going to give the chiral symmetry of the fermion partners of the Higgs to the Higgs, and so that has to erase this sensitivity on higher scales. And sure enough, when we do the actual calculation, we find that it does. It's canceled order by these new partner particles. Now, if we've broken supersymmetry, if we've softly broken it by introducing masses to the scalars, the cancellation of the quadratic divergences will still persist, but now there will be an extra contribution from this loop that's finite, corresponding to the fact that the stops in this loop don't have the same masses as the tops. Okay, so the extra contribution coming from that, it's actually not totally finite, it's logarithmically divergent, but if you write down a full theory of how you broke supersymmetry, even that logarithmic divergence is taken care of. Okay, so what you see is, if you've broken supersymmetry in the soft way by adding masses to the new scalar partner particles, the complete UV sensitivity vanishes. You're no longer wildly sensitive in the UV. You can now predict the Higgs mass. And you predict it in terms of contributions that are proportional to the masses of these new particles. So when I told you that taking the ambitious solution to the hierarchy problem, trying to make the Higgs mass parameter finite and calculable, was the best way to see the hierarchy problem, this is really it. Right? You no longer have to worry about UV sensitive quantities that depend on your regularization. You have finite or at most logarithmically UV sensitive contributions that are proportional to the masses of the new particles that made the Higgs mass finite. Okay. This is how you see the hierarchy problem, right? If I make these new particles arbitrarily heavy, each one of them gives some enormous contribution to the Higgs that must cancel to high precision. Okay. So a good way if someone tells you that they don't think there's a hierarchy problem is to say, give me any theory in which you can calculate the Higgs mass, and tell me what your answer is if all the particles are much heavier than the weak scale. All right. So that's all I want to say about supersymmetry. It makes me a little sad to have done all of that in 10 minutes. When I was trained as a graduate student, I first learned about the standard model by learning about the minimal supersymmetric extension of the standard model, and then taking out all the superpartners. So it's a sign that times have changed a little bit. The supersymmetry is a beautiful theory, not just as an application to the hierarchy problem, but also as a way of understanding the properties of gauge theories. And Yael will tell you a lot more next week about how supersymmetry works in that context. Okay, so now let me turn to global symmetry. It works in a very similar way to supersymmetry. So the idea is there will be a symmetry. You extend the standard model to involve a new symmetry. That symmetry is manifest when the Higgs mass parameter goes to 0. And so it makes the Higgs mass parameter technically natural. And it's just using the other symmetry option available to us. Moreover, just like with supersymmetry, because we haven't seen additional particles degenerate with their standard model counterparts, we have to break the symmetry by some amount, with a soft breaking, with some dimensionful parameter. And so that means there will now be finite and calculable contributions to the Higgs mass that come from however much heavier we've made these new partner particles. So the basic idea of a global symmetry solution to the hierarchy problem is that the Higgs is a pseudo-Goldstone boson, or Goldstone boson, of the spontaneous breaking of some larger symmetry. Okay? And that larger symmetry includes, as a subgroup, some gauging corresponding to the Electroweak group in the standard model. So ultimately, if you want to do this carefully in the standard model and respect what Michael has alluded to, the custodial symmetries of the Higgs sector, that actually turns out to constrain the patterns of symmetry breaking quite robustly. I just want to give you the simplest example of how it might work. So the simplest example of how it might work is to just imagine taking a global symmetry SU3 and spontaneously breaking it to SU2. And then you imagine gauging this SU2. So you can think about gauging the SU2 by just turning on couplings of SU2 weak gauge bosons to the currents of that global symmetry. Okay. So the Higgs now we want to imagine is a Goldstone boson coming from the spontaneous breaking of SU3 to SU2. Again, I want to emphasize this specific example is not phenomenologically viable because of precision Electroweak constraints, but it's the simplest way to see how these theories work. Okay. So we imagine this breaking happens because of the vacuum expectation value of some scalar I'll call phi that transforms as a fundamental into the SU3, and I'll call that order parameter f. Okay. So if we just want to understand the low energy theory of Goldstone bosons coming from this pattern of symmetry breakings, we can just expand phi in terms of the Goldstones. Okay, so we can ignore the radial mode. That's new physics at this higher scale f. We're not worried about that. We want to understand what happens with the Higgs, which is a Goldstone. So we expand this in terms of some Goldstone modes. I'll pick some basis where the vev for phi is in the lowest component of the SU3 fundamental vector. And so we can just write this out explicitly. I find with all of these global symmetry arguments, it's often very helpful to just write things out explicitly. If it gets confusing as to what's going on, just multiply some matrices. OK, so the Goldstones live. There's one Goldstone that's going to be a singlet under the standard model that I'm not going to be interested in. But I'll write it down here for completeness. I'll call that guy eta. And then, well, I'm already writing the answer here, but just to make sure everyone's awake, how many Goldstones do I expect from SU3 breaking to SU2? 5. Good. I expect 5 Goldstones corresponding to the number of broken generators. So I expect 5 real degrees of freedom. Okay, and so one of them corresponding to the generators on the diagonal, I'll call eta. That's going to be irrelevant for our discussion. We'll ignore it. And the remaining 4, okay, will organize themselves into a complex doublet under the unbroken SU2. Okay, so you can go ahead and convince yourself, and I leave it in the notes so you can see it in detail. You can convince yourself that indeed these fields combine themselves into a complex doublet that transforms as a doublet under the unbroken SU2. So that makes it a perfect candidate if we imagine gauging this SU2 and identifying this with SU2 left of the standard model. Then what we would have made was a Goldstone multiplet that transforms into fundamental under the SU2. All right. So that really seems like something that we can identify with the Higgs boson. So it transforms as a doublet under the unbroken symmetry, the SU2. And at least to leading order, these Goldstones all transform with a shift with respect to symmetry transformations under the broken generators. So they're Goldstones. There's a shift symmetry. And that shift symmetry prevents you from writing down a mass term for them. Right? So it's a shift symmetry now that is manifest when the Higgs mass is 0 that makes the Higgs mass parameter technically natural. OK. Some interesting implications follow immediately from the statement that the Higgs is a Goldstone boson. So you can go ahead, for example, you can say, if I started just in the simple linear sigma model parameterization, if I ask how the kinetic term of this field phi descends into derivative interactions for the Goldstones, this is an exercise that I encourage you to do for yourself, keeping track of a normalization factor that I've been a little careless about. If you take the kinetic term for the scalar in the linear sigma model and you expand it out in terms of these Goldstones, what you get is at leading order, you get a kinetic term. So that's good. But then what's forced upon you by expanding out the exponential is you get an infinite tower of irrelevant operators, all right, non-normalizable operators that are also forced upon you just by the structure of symmetry breaking. So the leading thing that you actually get by expanding out in the exponentials is something of the form h squared d mu h squared. And you can calculate this as a 1 over 2 times the scale f squared. And then there are other terms that appear suppressed by higher powers of f. All right. So this is unavoidable. If the Higgs is a Goldstone boson, the existence of these interactions is unavoidable. Okay? And that has 2 very beautiful, interesting implications. The first implication is that there will be deviations in Higgs parameters with respect to the standard model predictions. As Michael told you this morning, the standard model by construction is the most general set of renormalizable interactions allowed by gauge invariance in the particle content of the standard model. But you could imagine deviating from the standard model by introducing irrelevant operators. And the idea here is in the low energy effective theory, those operators are forced upon you. As Michael will tell you tomorrow morning, these operators change the properties of the Higgs boson with respect to their standard model predictions. In fact, this operator does something really cool. When you break electroweak symmetry, this actually gives you what looks like a shift in the wave function normalization of the physical Higgs. And so it has the property of suppressing all Higgs couplings to standard model particles by the same amount. All right, this is a very interesting effect. It's very hard to pin down. It turns out the best thing you should do to discover this effect is to build a lepton collider. It's very hard to look for at the LHC. But there's this beautiful idea then that Higgs coupling deviations at tree level are an unavoidable prediction of a global symmetry solution to the hierarchy problem. The second thing that's sort of forced upon you by looking at these interactions is that your UV completion of this theory can't just be the global symmetry itself. So even if we hadn't had some linear sigma model here, some scalar that got a vev that broke the symmetry that gave us the goldstones, even if there was a more complicated pattern of symmetry breaking, in the low energy theory of the goldstones, there will be these irrelevant operators. And you can ask, if you want to have some well-behaved perturbation theory where you can do calculations at well-defined orders, you don't have to have infinite towers of irrelevant operators, that if you take these irrelevant operators, they contribute now, for example, to loop diagrams like the renormalization of the kinetic term. Okay. These things will contribute now. They'll have quadratic divergences integrated up to some cutoff. And so to have a well-behaved perturbation theory, including these irrelevant operators, it tells you that this low energy description of the goldstones have to have some UV completion that enters before about 4 pi times the scale f. Okay. So even if there wasn't, there are lots of things that could happen to UV complete the Higgs as a Goldstone boson. One of them is it could just be a linear sigma model, but it could also be that more complicated dynamics, such as some version of Technicolor, enters at a much higher scale. Okay. So composite Higgs models are theories where there's Technicolor that breaks SU3 to SU2 at some scale f, and then the Higgs is a Goldstone of that breaking. Now that's different from just Technicolor that breaks electroweak symmetry, right? Because now the Technicolor is giving you the scale f, and then the weak scale is generated by the physics of the goldstones. Okay, so it's at a parametrically lower scale. All right. It's also possible that, in fact, what happens at the scale is just there's some weakly coupled scalar degree of freedom. It's just a linear sigma model. And then you have to solve the hierarchy problem for the linear sigma model. So we normally imagine doing that with supersymmetry. There's a third option that has not been maximally explored, which is that it's called turtles. Turtles comes to us, the term turtles comes to us from Hindu mythology, courtesy of Hawking. The idea is that that there's the weak scale comes because the Higgses are goldstones from a pattern of symmetry breaking at the scale f. There's a scalar at the scale f that does that symmetry breaking. That scalar is the goldstone of yet another pattern of spontaneous symmetry breaking from another scalar at a higher scale, and so on and so forth, all the way up to the Planck scale. Okay, so it's turtles all the way down. That turns out to be hard to do in practice, but it is a not fully developed direction of model building. So if you're looking for something fun to do, go read about turtles. Okay. So as the story that I've told you, the Higgs is just a Goldstone boson of the spontaneous breaking of SU3 across SU2. I haven't turned on any standard model couplings for this Goldstone boson. And in particular, if I just write down the normal Yukawa couplings of the Higgs to standard model fermions, that breaks the global symmetry of which the Higgs is a Goldstone. So you'd expect the Yukawa couplings in this simple story, the Yukawa couplings would still have these quadratic divergences and this UV sensitivity. So you can get rid of that by extending the symmetry to act not just on the Higgs, on the scalar sector, but also extending it to act on the fermions. So now you take every fermion in the standard model, say that transforms under SU2, and you add an extra degree of freedom so that the whole multiplet transforms under SU3. Now you can write down a Yukawa coupling that is SU3 invariant, and as such, because it's an invariant to the original symmetry, it will not give a potential to the Goldstone. Okay. So if you really want to make this work and reduce the UV sensitivity, you extend all the degrees of freedom in the standard model to transform under multiplets of the original symmetry. Now that tells you, just as in supersymmetry we had new partner particles, in this theory we now have new partner particles. They're the new symmetry partners of all the standard model fields. And because we haven't seen them degenerate with their standard model partners, we have to give them a little extra mass to make them heavier. And now that means there are loop diagrams that cancel the quadratic divergences, but there's a finite piece left over, just as in supersymmetry. Okay. So I go through an example of that in detail in the notes that I'll post later this afternoon. It's a fun exercise to work out in the global symmetry case, but it works exactly like in supersymmetry. There's new partner particles that are required to cancel the UV divergences. You give them a little mass to explain why we haven't seen them yet, and now the Higgs mass parameter gets a correction proportional to the masses of the new particles. Okay. So both of these symmetry solutions work in the way you like. You can now predict the Higgs mass, but you do so at the price of having new particles charged under the standard model whose masses contribute in a finite way to the Higgs mass. All right. Any questions about global symmetry solutions, the hierarchy problem? No. Everyone, we're now in the sleepy period of the afternoon. Okay. All right. So I want to end with the last sort of conventional approach to the hierarchy problem. It's not really conventional. It's quite controversial. But it is one of the pillars of how people have thought about the hierarchy problem in the last few decades. And that is an anthropic explanation of the value of the weak scale. OK, so we already encountered an anthropic explanation for the cosmological constant. And the thing that I wanted to emphasize there was that it's only an explanation insofar as you make strong assumptions about what's allowed to vary between different universes in order to make observers. Okay. For the CC problem, the statement was that the cosmological constant couldn't be too big, otherwise we wouldn't make structure. But that required us to assume that the spectrum of primordial density perturbations was not any larger than we see it in our universe. If it was, we wouldn't have a bound. So what's the anthropic explanation for the weak scale? Well, let's go through some nice fun parametrics of how things scale in the standard model. Okay, so in what follows, I'm going to imagine we're not going to talk directly about the Higgs mass parameter. We're going to talk about the scale of electroweak symmetry breaking, which if we imagine the quartic is held fixed, that's directly related to the Higgs mass. Okay, so we're going to imagine that we can vary that scale relative to the actual value that we observe in the standard model, which is 246 GeV, depending on your conventions. OK, so the first thing that you can do is you can work out, if I allowed the scale of electroweak symmetry breaking to vary relative to what we see in the standard model, how would the mass splitting between the neutron and the proton change? OK, so how are the neutron and the proton different? Come on, this is a softball. What's that? Quark content. Good. So what's the difference in the quark content? Good. OK, so yeah, we're talking about up quarks and down quarks. Now, of course, that's a small we know when you first learn about the strong interactions, the first thing people tell you is most of the mass of the proton and the neutron does not come from the quarks, right? It comes from confinement in this zoo of virtual particles. But there is a contribution coming from the valence quarks. And so there are different valence quarks with different masses. And so there's a contribution to the mass splitting that depends on the Higgs vev. OK, so the mass splitting between the neutrons and the protons, there's the piece that comes from the fact that there are different quarks. OK, so written in terms of the Higgs vev relative to the standard model, that's this piece. Then there's also an electromagnetic splitting because the proton is charged and the neutron is not. So there's also a contribution to the mass difference coming from electromagnetic loops. So that is independent of the Higgs vev. And this is all in big M EV. OK? So obviously, if I start to vary the weak scale relative to the observed value, I'm going to change the neutron-proton mass splitting. OK? All right, so as it is at least in the standard model, right, if we have free neutrons are not stable. They decay into protons because they can. OK? And so the reaction energy is just the difference, of course, between the neutrons go to a proton and electron. So the mass splitting is the difference between the neutron mass, the proton mass, the electron mass. All right, and so it's just subtracting out the electron mass. That gives us 2.5 V over V standard model minus 1.7 MeV. Now, what stabilizes the neutron? Do neutrons just decay all over the place inside you right now? Are you full of rapidly decaying neutrons? Yes.
Are you talking about within nuclei?
Yes, yeah.
Yeah, the Fermi statistics.
So there are nuclear binding energies, right? OK, so there are nuclear binding energies. The theory of calculating nuclear binding energies is complicated. But there's at least a long-range part of the nucleon-nucleon potential that you can mock up due to single pion exchange. Okay, that in some sense is the leading contribution to nuclear binding energies. Now, so that means that the force, the range of the nuclear binding energies, that long-range force, it goes inversely with the pion mass. And the pion mass, famously, pions as goldstones would be massless. If the quarks didn't have masses, they get mass because the quarks do have masses. OK, so the pion mass scales like the square root of the quark masses. And that means that the nuclear binding energies have some dependence on the values of electroweak symmetry breaking. Yes, yes.
Little small.
In all of this, all I'm doing is allowing myself to vary v and keeping the Yukawas fixed. And of course, you anticipate the reason why this argument is not airtight. Okay, good. So I will get to that conclusion momentarily, but I am getting there. I am no more a fan of this principle than I am of the explanation for the CC. Okay, but okay, so you can calculate the binding energy. Okay, it goes like there's some piece that is not well approximated by this pion exchange. All right, so that's something that we're just going to treat as constant. And then there's going to be a piece that does depend on the pion exchange. It has dependence on the difference in the VEV relative to the standard model coming from the dependence in the pion masses. And this is also an MEV. OK. So now you can see if you allowed yourself to increase the value of the weak scale relative to the standard model value, you would very quickly reach a point where the binding energy was now smaller than the reaction energy, and you would no longer be stabilizing neutrons inside nuclei, right? So now, instead of you being made up of mostly stable nuclei, you would be undergoing all sorts of interesting decay processes, and you probably, you would imagine a much less forming life like you and me. You would have a very hard time forming any complicated atomic structures, just because you could never form any particularly complicated nuclei, because the neutrons would all rapidly decay. Okay? It turns out if you just study it for the simplest system, so this binding energy is an approximation of the binding energy in deuterium, where the pion exchange is a good approximation. It actually turns out you hit this inequality if you make V over V standard model much greater than 1.2 times its observed value. This seems like a very strong bound, right? If you made the weak scale even 20% larger than the value we see, seems like an innocuously small change. Suddenly, neutrons would be unstable. Okay. Now, this is in deuterons. Maybe the universe doesn't go crazy if you can't form deuterons. You can make a version of this argument in more complicated nuclei where the binding energy has different dependence. And there, the bound that you find is that you can't get much greater than about 5 times the value of the weak scale before neutrons become unstable to decay within nuclei. So this is what's known as the atomic principle. As an anthropic argument that you could bound the weak scale by at least requiring that neutrons be stabilized within nuclei. It's due to Agrawal, Barr, Donahue, and Seckel. OK, and so you would imagine, just as you did for the CC, that if there were many different universes, where in every universe there were many different contributions to the Higgs mass parameter in the ultraviolet, at least in some of those universes, just statistically speaking, even if all of the contributions are of order of m Planck, there'd be some universe where on the tail of the distribution, they just happen to statistically cancel out to the value of the weak scale that we see. Only in those universes would neutrons be stabilized within nuclei, and you could form people out of them. And so that would be now an anthropic explanation. We can only show up in those rare universes that satisfy this bound. Now, just as the anthropic explanation for the CC was unsatisfying because we held other things fixed, here Matthias has anticipated the problem in the argument is I haven't allowed the Yukawa couplings to vary, right? These rules, these relationships only hold if the Yukawa couplings are held fixed. But if I allow the Yukawa couplings to vary, now everything changes, right? So it changes here in the proton-neutron mass splitting. It also changes, of course, in the binding energies because it appears in the pion masses. And so it's easy to imagine a universe where, sure, I can allow the weak scale to be much larger than its observed value, as long as I also pick other values of the Yukawa couplings. OK. So only by making a very strong assumption, it seems to me incredibly strong to assume that somehow in all universes the Yukawas are the same, right? Only the contributions to dimensional parameters vary. Only by making that strong assumption do I get a bound. OK. So to me, it's unsatisfying. To other people, it's more satisfying. I simply present it to you as an argument for you to understand so that you can come to your own conclusions. In fact, people have argued that it's completely possible to construct a weakless version of the standard model where the low energy symmetries are just the ones that we see at low energies. In other words, where it's just SU3 color times U1 electromagnetism. So the claim is that everything, if your standard model just consisted of those symmetries and particles transforming under them, that you could have everything happen as normal. Now, you have changed physics in the universe very importantly because now you no longer have weak nuclear decays. Weak nuclear decays are important for some things, right? But the claim is that it's possible to imagine a universe where baryons form, stars form, planets form, where without ever having had SU2 at low energies. And that would also be, of course, a falsification of this argument, right? Then you would never have to worry about the value of the weak scale. Okay. So take it as you will. So these were the sort of conventional approaches to the hierarchy problem that held sway over the last 40 years. They're all beautiful and interesting ideas, and I encourage you to explore them more in your own time. And then tomorrow I want to turn to the newer ideas that have come up. And why have they come up? Well, we've already talked about why lower cutoff solutions is disfavored, because we don't see anything right at the Higgs mass. But even the symmetry solutions to the hierarchy problem, they predict these new partner particles. These new partner particles are charged into the standard model, because both supersymmetry and the global symmetry commute with the standard model gauge groups. And we can't make those partner particles arbitrarily heavy without giving fine-tuning to the weak scale again. So at the LHC, we're now probing multi-TeV. We have yet to see any evidence for those particles. And so the naturalness of those explanations is now becoming at least somewhat tense. And so that's inspired over the last 5 or 6 years a lot of activity to try to come up with novel ways of solving the hierarchy problem that explain why we haven't seen anything yet, but still allow us to understand why the Higgs mass is small. So thanks very much. Yeah.
What about scale symmetry? Usually that's also one of the solutions to the
Right. And so you'll notice when I told you the cartoon sketch of the Coleman-Manjula theorem, right, that in addition, so for massless particles, conformal symmetry was also allowed. What do I want to say about conformal symmetry? So people have used conformal symmetry in lots of different ways as statements about the hierarchy problem. If conformal symmetry is an exact symmetry of the standard model in the ultraviolet, you've sort of trivialized the hierarchy problem because there's no mass scales in the ultraviolet. Okay. To me, that's not satisfying because there is some scale associated with the physics of quantum gravity. Quantum gravity has no reason to respect conformal symmetry of some field theory. Okay, and so in some sense, to me, that just doesn't actually cohere as a solution. I don't care if the standard model reaches a conformal fixed point, because that still doesn't explain why there wasn't some large mass parameter in the UV of the theory. That should still be there. Okay. A more ambitious thing you could try to do is imagine there really is a scale in the ultraviolet. Okay, the standard model is generated in the ultraviolet. A bunch of other things are generated in the ultraviolet. The standard model plus other things flows to a conformal fixed point, where at the conformal fixed point, all of these other mass scales that would contribute to the Higgs mass cancel out, okay, because of the values of the couplings at the fixed point, all right? That would allow you to explain miraculously why there's a light scalar that comes out at the end of the day, despite there being scales in the ultraviolet. That would be, to me, a real conformal symmetry solution to the hierarchy problem, because it says, I admit that there are scales in the UV, right? I don't trivialize the problem. But I somehow erase the sensitivity to those scales by the properties of my conformal fixed point. And then you exit the conformal fixed point right above the weak scale, right, so that you don't accumulate any extra UV sensitivity. And so that would be a potentially viable solution. Now, what do you have to explain in that theory? You have to explain why the fixed point values of the couplings, which are the ones that control the size of these corrections of the Higgs mass, why they conspired in such a way to make the Higgs light. Okay, that seems like it requires a conspiracy between the scales in the UV and the couplings of the fixed point. Now, what could conspiracies be? They could be UVIR mixing, right? Something in the theory makes the couplings know about the scales. Okay, that's a possibility. Okay, so that's a very hard problem. All right, there are easier ways to talk about conformal symmetry. I would say those don't actually solve the hierarchy problem. Okay.
ignoring gravity is...
Ignoring, it's putting away the problem, right? I mean, it's yeah.